Today, we're exploring a topic that's all about balancing multiple conditions at once: systems of linear inequalities. Imagine you're running a business, organizing an event, or managing resources, and you have several conditions that need to be met. Systems of linear inequalities let us take these real-world restrictions, like budget limits, time constraints, or minimum requirements, and represent them mathematically. In this lesson, we'll break down how to set up these systems of inequalities and graph them, so you can see all possible solutions that meet every condition at once. Let's dive in and see how it works. Now that we understand what systems of linear inequalities are, let's explore how to set them up and graph them. When working with systems of inequalities, our goal is to find all values that meet multiple conditions simultaneously. Here's how we'll tackle it. The first step is to read each condition carefully and translate it into an inequality. For example, if a problem states, the total cost should be no more than $500, this translates to an inequality like y is less than or equal to 500. After translating each condition, we'll graph each inequality one at a time. Let's say we have these two inequalities. For each inequality, we will first draw the boundary line. Use a solid line for greater than or equal to and less than or equal to, meaning the boundary is included in the solution. Use a dashed line for greater than and less than, meaning the boundary isn't included. Next, we shade the solution region by determining which side of the boundary line represents the solution by testing a point, like 0, 0, unless it's on the line. Once each inequality is graphed, we look for the overlapping shaded area, or the intersection, where all inequalities are satisfied at once. This shaded region represents all possible values of x and y that meet the system's requirements. This shaded intersection represents all combinations of x and y that satisfy every inequality in the system. This solution set can help answer questions about what values meet all conditions simultaneously. By following these steps, you'll be able to set up, graph, and interpret systems of linear inequalities to find the range of solutions that satisfy all constraints. Now, let's practice with some examples. A school fundraiser wants to raise at least $1,000 by selling two types of tickets: student tickets and adult tickets. Student tickets are priced at $5 each, and adult tickets are priced at $10 each. Additionally, they plan to sell no more than 200 tickets in total. Let x represent the number of student tickets and y represent the number of adult tickets. Write and graph a system of inequalities that represents these conditions. First, let's write the inequalities that represent the conditions. We already know that x represents the number of student tickets and y represents the number of adult tickets. The problem states that the fundraiser needs to raise at least $1,000. Since each student ticket costs $5 and each adult ticket costs $10, we can write the total revenue as 5x plus 10y. To meet the goal of at least $1,000, our first inequality becomes the following. The second condition states that no more than 200 tickets will be sold. This means the total number of student and adult tickets combined should be at most 200. We can write this inequality as follows. Now we have a system of two inequalities. One that represents the total revenue and one that represents the total number of tickets sold. Next, we'll graph each inequality on the coordinate plane. Let's start with the first inequality. To graph this inequality, let's first rewrite it in slope-intercept form: y equals mx plus b. While we're at it, let's do the same for the second inequality. Now, we'll plot the first inequality on a coordinate plane, using a solid line since greater than or equal to includes the boundary line. Then, we'll shade above the line to represent the region where y is greater than or equal to -1/2 x plus 100. Next, we'll plot the second inequality on the same coordinate plane, still using a solid line. Then, we'll shade below the line to represent the region where y is less than or equal to -1/2 x plus 200. To find the solution to the system, we look for the region where the shaded areas from both inequalities overlap. This intersection is the solution set, representing all combinations of student and adult tickets that meet both the revenue and ticket limit requirements. And so, these are our final answers. This system represents all possible values of x and y that meet the school's goals. The overlapping region on the graph shows the combinations of student and adult tickets that ensure both conditions are satisfied. Let's now discuss a more challenging example. A factory makes two types of products, A and B. Product A requires 2 hours of labor and 1 unit of material, while product B requires 1 hour of labor and 3 units of material. The factory has at most 8 hours of labor available and no more than 9 units of material. Additionally, they need to produce at least 2 units of product A to meet demand. Let X represent the number of units of product A and Y represent the number of units of product B. Which of the following systems of inequalities best represents these conditions? Let's begin by setting up each inequality based on the conditions given. First is the labor constraint. Each unit of product A requires 2 hours of labor, and each unit of product B requires 1 hour of labor. Together, we can write the labor constraint as follows. Next is the material constraint. Each unit of product A requires 1 unit of material, and each unit of product B requires 3 units of material. The total material used should not exceed 9 units, so we write it as follows. Finally, we know the factory must produce at least 2 units of product A, so we have X greater or equal to 2. Now that we have our system of inequalities, let's graph each inequality one at a time, starting with the labor inequality. Let's first convert this into slope-intercept form for easier graphing. Next, we'll plot this inequality using a solid line because less than or equal to includes the boundary line. Then we'll shade below the line to show all points where y is less than or equal to negative 2x plus 8. Now we'll graph the second inequality. Let's first convert this into slope-intercept form for easier graphing. Next, we'll plot it with a solid line and shade below it to show the solution region for y is less than or equal to negative 1/3 x plus 3. Finally, we'll graph the third inequality which describes the production requirement. The inequality x is greater than or equal to 2 represents a vertical line at x equals 2. Since we're looking for values where x is greater than or equal to 2, we'll shade to the right of this line. To find the solution to this system, we now look for the region where the shaded areas from all three inequalities overlap. This intersection is the solution region that satisfies the labor, material, and minimum production requirements. Thus, from the graph and inequalities we got, the correct solution is option A. Great work today! Let's quickly review the key concepts we covered while solving systems of linear inequalities. First, we learned to translate phrases like at least, no more than, and greater than into mathematical inequalities. Next, we learned that each inequality needs its own boundary line and shaded region on the graph. Remember, solid lines for greater than or equal to and less than or equal to, and dashed lines for greater than or less than. Testing a point, like 0, 0, helps determine which side to shade. Once each inequality is graphed, the intersection of the shaded areas represents the solution region for the system. This area meets all conditions, showing the range of possible solutions. This overlapping shaded region contains all values of x and y that satisfy every inequality in the system. In real-world terms, this region represents all possible outcomes that meet every condition of a problem. With these steps, you're ready to approach any system of linear inequalities. Remember, the key is to carefully translate each condition, graph it, and find the intersection of all solution regions. Keep practicing, and see you next time.